Turbine power plant operates on the simple Brayton cycle between the pressure limits of 100 and 1600 kilopascal. The working fluid is air, which enters the compressor at 40 degrees centigrade at a rate of 850 meter cube per minute and leaves the turbine at 650 degrees centigrade. Assuming a compressor and isotropic efficiency of 85% and a turbine isentropic efficiency of 88%, determine the net power output. We have to find the net power output, the backwork ratio, the backwork ratio, and the thermal efficiency. Use the constant specific heats with Cv is equals to 0.821 kilojoule per kg dot K. Cn is equals to 1.108 kilojoule per kg dot K and use the value of K is equals to 1.35. So this is the question. The properties of air. We have written over here. We will draw the TNS diagram for this question. That is like this. This is 0.4, 3, 2, and 1. This is the heat input and this is the output heat. Here is the temperature is 313 Kelvin and here the temperature is 923 Kelvin. So for the compression process, Rp is equals to P2 divided by P1, that is equals to 1600 kilopascal divided by 100 kilopascal. This would be 16. And temperature T2S is equals to T1 into P2 divided by P1. Power K minus 1 divided by K. That is equals to 313 into 16 power 0.35 divided by 1.35. That is equals to 642.3 Kelvin. And temperature T2 is 642.3 Kelvin. Now I'll further solve the question. For the efficiency is given as H2S minus H1 divided by H2 minus H1. This is equals to Cp into T2S minus T1 divided by Cp into T2 minus T1. This will give us T2 is equals to T1 plus T2S minus T1 eta C. Now we'll put the values. We have 313 plus 642.3 minus 313 divided by 0.85. This is equals to 700.4 Kelvin. Now for the expansion process. T4s is equals to T3 into P4 divided by P3 power k minus 1 divided by k, that is equals to T3 into 1 by 16 power 0.35 divided by 1.35. This will come out to be 0.4873 T3. Now the thermal efficiency, eta T is equals to H3 minus H4 divided by H3 minus H4s. This is equals to Cp into T3 minus T4 divided by Cp into T3 minus T4s. That is equals to T4 is equals to T3 minus eta T into T3 minus T. Now we will put the values over here. Here T4 is 923. That is equals to T3 minus 0.88 into T3 minus 0.4873 T3. Here T3 is taken as common. From here we will take T3 as common. And from here we get by solving this further, we will get the value of T3, that is 1682 Kelvin. Now the mass flow rate is calculated as M is equals to P1V1 over RT1, that is 100 into 850 divided by 60. Divided by RT1. R is 0.287 and T1 is 40 plus 273. The answer comes out to be 15.77. This is 15.77 kilo kg per second. The net power is now the net power is calculated as net power output is WC equals to MCP into T2 minus T1, that is equals to 15.77 into 0.821 into 700.4 minus 313, that is equals to 6769 kilowatt. Now the net power WT output is calculated as MCP into T3 minus T4, that is equals to 15.77 into 0.8211682 minus 923, that is equals to 13257 kilowatt. So now the net power output is equals to, first we calculate the power input and power output. Now we will calculate the net power. That is WT net is equals to WT out minus WC in. That is equals to 13257 minus 696769, that is equals to 6488 kilowatt. So now the backlog ratio is calculated as RWBW, that is WCN over W out, that is equals to 6769 divided by 13 comma 257, that is equals to 0.511. Now the rate of heat input. Now Q in is calculated as MCP is equals to T3 minus T2, that is 15.77 into 0.821 into 1682 minus 700.4, that is equals to 17,147 kilowatt. Now the thermal efficiency is calculated as W net is equals to Q in, that is 6488 divided by 17,147, that is equals to 0.378, that is 37.8%. This is our answer. Thank you.